Our project is implementation and evaluation of the Semantic-Object SLAM algorithm. Object SLAM is a framework which focuses on using objects in the environment for SLAM. It considers the object's position, orientation, and occupied space. Objects are found using 2D object detection. Early object SLAM frameworks represented objects as cuboids. In 2019, Nicholson proposed quadric SLAM, which represents objects as ellipsoids instead. The advantage to this is that objects can be represented more compactly and can be easily projected onto the plane as an ellipse. Semantic-Object SLAM, or SO-SLAM, was proposed by Lau in 2021. It builds on top of the quadric SLAM framework by adding constraints on the object using knowledge about what man-made objects typically look like. We'll discuss these constraints in the following slides. SO-SLAM takes in 2D detected images and associates it with odometry data to decide whether we've seen a new object or an existing one. If it is new, then we initialize a new ellipsoid using some of the constraints. If it's old, then we optimize its shape and pose using additional constraints. The optimized factor graph will then give us both estimated ellipsoids for the objects and optimized camera poses. While Lau described this algorithm, there is still no open source implementation. Our contribution is to provide such an implementation so that it can be evaluated. To evaluate the algorithm, we used images from 3 different TOM RGBD scenes. These datasets are indoors and feature many man-made objects, which is the main use case for SO-SLAM. We use both estimated odometry data using the ORB-SLAM2 algorithm and ground truth odometry. Image detection is done with YOLO to give a semantic prior on the objects. Data association was done by hand.
We propose a novel method for initializing a 3D ellipsoid for each detected object in the environment using a single RGB image input. The ellipsoid is defined by its radius, position, and orientation, represented by a vector R and matrix Z. To combine these parameters, we introduce a 4x4 triangular matrix Q, which has 9 degrees of freedom. By imposing sufficient constraints, we ensure that the ellipsoid is initialized with the correct shape and pose. We can extract the bounding box from the input image, which enables us to restrict the size and position of the ellipsoid accordingly. By projecting the ellipsoid onto a 2D image plane, we can employ the camera matrix P to compute the parameter matrix of the ellipse. Subsequently, we can determine the minimum rectangle of the ellipse and perform an arrow analysis by comparing it with the bounding box. We can obtain information about an object's category from the input image. Objects display particular proportional relationships between their dimensions, which can be predicted based on an object's semantic prior. We use a lookup table with ratios corresponding to different semantic labels. For example, for a keyboard, we set the expected ratios for its x and y dimensions to be 10 and 20. The following 2 images show the results before and after applying semantic scale constraint. As can be seen, it effectively corrects the shape of the keyboard.
The next constraint we use is the plane supporting constraint. For example, most objects rest on flat surfaces, such as floor or desk. Therefore, the XY orientation of the objects are usually orthogonal to the normal vector of the plane. We then measure the error. Additionally, this constraint is flexible, allowing us to adjust it based on an object's semantic prior. Like in the case of a drone, we will not use this constraint. Here is the initialization result. By minimizing the 3 aforementioned constraints, the bounding box, semantic scale, and supporting plane, we can derive the optimal ellipsoid of each object. We employ the LM algorithm to solve this nonlinear problem and get the result of our single frame initialization method. As shown in the front view and the point cloud, the ellipsoid effectively captures the shape, position, and orientation of the 3D object.
The plot shows the full factor graph in our optimization process. We use odometry data as prior for each pose and motion model for factor between poses. In the camera pose and quadrics optimization process, we add a new factor called symmetry factor to constrain ellipsoid direction and rotation. Then we use 4 factors, odometry data, and motion model to optimize the quadrics and camera poses simultaneously. It is common that human-made objects are symmetrical that we use a symmetry factor to constrain our ellipsoid's direction. However, we have to extract the 3D symmetric points from the 2D monocular image to verify the object is symmetrical. The plot shows that the points are symmetrical in the world coordinate, but not on the image. So we find the 3D distance between sample point and nearest edge point to be our descriptor to optimize those functions. To reduce the computation cost, we assume that in the 2D space, the nearest edge point UE is also the nearest edge point VE in the 3D space after a 2D to 3D linear operator. Since the ellipsoid is symmetrical, we can find the symmetry sample point in 3D space, then project it to the 2D to find the nearest edge point. Finally, we project symmetry edge point to 3D, then we can get the arrow.
We use the Framework 2 digits TUM RGBD dataset to test our algorithm. We use Pangolin and OpenGL to visualize the outcome. We use multi-thread to improve efficiency. One thread is for visualization and the other is for SLAM calculation. We visualize the estimated ellipsoids and the point cloud in 3D space and visualize the detection bounding box projected ellipse on input images. We hand-annotated the ground truth ellipsoids based on visualization and point clouds and used them to evaluate our algorithm. We implement some visualization content control, for example, camera, keyframe, ground truth, and direct view from XYZ axis, and we can turn off their visualization accordingly. We also implemented visual evaluation method, as shown above, are the rotation error and IOU of ellipsoids. Rotation error checks the yaw, pitch, and roll error between estimates and ground truth. IOU is the intersection over union of two ellipsoids volume. Thanks to ground support vector, the rotation error is rather small, and the error is mainly came from the yaw axis.
So thanks for listening, and you can ask any questions regarding the details of the project.